We will move on to our next speaker, Geert from Com&Sens. He will also demonstrate the use of online monitoring techniques using fiber Bragg grating sensors.
Good morning, everybody. My name is Geert. I'm the co-founder of Com&Sens, and I'm going to talk to you about the work that Com&Sens has been doing within Qualify. And it's about using fiber Bragg gratings to monitor the health of a bonded joint. Well, first, let me talk to you about the content. In the content, we are going to talk about Com&Sens, about some requirements for the monitoring system. We're also going to talk to you about the testing we have been doing in Qualify, and then jump to future work. But first, a few slides on Com&Sens. So who are we? Well, Com&Sens designs optical fiber sensors for harsh environments. So we use purely optical fiber sensor and we attach it or embed it in different materials. Can be steel structures, can be concrete, asphalt, or composites. And in Qualify, we combine composites with steel structures in a hybrid joint. We are the forerunners in fiber optic sensing, as such that we use reinforced optical fiber sensors, but I'm going to talk to you about that a little bit more in detail later on. And we attach or embed those optical fiber sensors in many industries. Civil engineering can be one, but within Qualify, this is the marine industry. What is now the role of Com&Sens within Qualify? Well, we foresee the monitoring system of the bond line with optical fiber sensors, and we like to monitor the deformations of that bonded joint, so over the length of that bonded joint, but we also like to detect the crack which occur in a bonded joint that it's maximally loaded. And of course, what we need to do is we need sensors that fit the purpose. And that means that we have to look in a marine environment. On the picture below, you can see a ship which is consisting of a hull and a superstructure which is in composite. So you have a bond between the composite structure and the hull. And here you have the bond line, which we like to monitor. But first, let's talk to you about the sensor principle. Well, the sensor principle is fiber Bragg ratings, and the principle is as followed, which is seen in this movie. You have an optical fiber, in which a fiber Bragg rating is inscribed. Such a fiber Bragg rating has a typical length of about 8 millimeter, can be less, can be a little bit more, and what happens now once this is inscribed, if you couple in light into that optical fiber with different wavelengths, what we see is that a single wavelength is interacting with the fiber Bragg rating and is back reflected, and the rest of the light is transmitted. If you now strain the fiber, what you will see is that back reflected peak will change over time. And by following up the change of that Bragg peak, you can follow up the strain of the optical fiber. As such, if you attach the optical fiber to a structure, you will be able to monitor the strain or the deformation of that structure. The big advantage over classical strain gauges is that you can have multiple points in a single fiber. So if you would look at this picture, and you know that there's 6 electrical strain gauges installed, you already get a lot of wiring of that electrical strain gauge, while for an optical fiber, this is not the case. As extra point is advantage is that the optical fiber or the fiber Bragg rating doesn't need any calibration or recalibration over time. So it's an absolute sensor, and it's a passive component. It only uses light. Then I go to the requirements needed for that monitoring system. We're talking about marine environment, so we're talking about seawater resistance. We're talking about temperature that can go up to 70 degrees C. We're talking about a good strain transfer, and we're also talking about optical fibers that need to be repairable. The system needs to be repairable and reliable. I'm not going to talk about seawater resistance. We did a lot of testing. However, it's not part of this presentation. But first, let's go to the sensor setup in Qualify. The sensor setup in Qualify, we, as Com&Sens, we don't use the optical fiber as such, but what in our own pultrusion process, we reinforce our optical fiber. And we do that or with flat strip or with a round rod. The advantage of doing so is that you create a robust sensor and you can also install it in really a fast manner. This will also be clear when we go to the in-field application within this presentation. For the sensor setup, if the installation is always the same thing, first you prepare the surface with a roughening and a cleaning step, then you place your sensor and then you glue it to the sensor. And then you can choose, or you place a protective tape or protective plate, but the choice there is more to protect the underlying baseline structure, then that you would protect the glue against seawater ingress, because it's also seawater resistance. You would use protective tape to prevent corrosion of your baseline structure. So temperature can go up as high as 70 degrees and perhaps even more. So we said, okay, let's try to adapt the raw materials of our pultrusion process and increase that heat deflection temperature of our pultruded rod, in which we succeeded during a lot of testing in our lab. And we went up to 102 degrees C for a curve of 15 centimeters. If you like to do absolute sensor measurements, you also need temperature compensation. This is not always needed, as you will see later on. If you go for event detection, this is not needed. If you need absolute sensor measurements, of course, this is needed. So part of the work within Qualify, we dedicated to temperature compensation, where we used our temperature compensation plates, or we used the temperature measurement directly and then compensated from the strains we are measuring on the structure. As an example, there is a curve given here where we used these samples. So we installed an optical fiber on a steel L profile. We used temperature compensation plates, but also temperature measurement. And what we did here was we compensate the strain of the L profile with the strain predicted by the temperature sensor. And then we get the absolute measurement. Strain transfer is an important one, as it is defined as how well the deformation of a structure is going to the sensor you are attaching to the structure. And in this case, we did a lot of testing on steel structure, GFRP structures, where we compared the strain we are measuring with more classical technologies. And we got some quite good results for that. Repairability is interesting, so it's also needed. In the beginning of the project, we said, okay, let's embed the optical fiber within the bond line or the composite material, and then if it breaks at the edge, we can still repair it. It's a patented technology that we further developed. So it's our own patented technology. It's developed in a clean room, and we decided to take it out from a clean room to a more industrial lab, and that we succeeded. And we also succeeded in an automatic alignment procedure and then brighting procedure. So how is it working? If you have a composite material with an optical fiber embedded, you have a connecting fiber on the outside, you align it to the internal optical fiber. Once it's perfectly aligned, you write your connection. Then I come to the bulk part of the presentation, which is on bonded joint testing, and we tested as well in the lab as in the field. I'm going to give you a few examples of the lab testing we have been doing and on how you can use the sensors to monitor cracks in those tests. And then I jump to the in-field applications. But first, the lab testing. So lab testing, we did tensile testing. That's what you see in this picture, is a tensile test on a complete joint. We also did Archon testing on a complete joint, and then we went for in-field testing. But first, the tensile test, we decided to use a loading cycle which progressively increases up to 75 and then up to breakage of the sample. The tensile test was done at Ghent University. In this case, you see how the sample looks like. In the next slide, we will show a little bit more in detail how it looks like. So this is it. So this is the bonded joint. The gray part is steel, and you have a lower joint and you have an upper joint. The blue is the glue, and the green is the composite material which is glued to the steel structure. On both sides, you have sensors, you have reference sensors, but you also have sensors on the bonded joint. You have sensors with an interdistance of 1 centimeter on the top and on the bottom joint, and that's shown here when it's installed. They are quite close to each other. Then we can start the measurement. And if we start the measurement, we see that for the bottom joint, which is not failed and which did not fail during the test, is that you get a nice, every time a nice increase of the strains measured on that bonded joint. If you would now look at the top joint, what you see is that from a certain point on, you get a crack and you see a lot of things happening with the sensors from sensor 1 up till sensor 5. These are the strain results, so the raw data. We can go up to process the results, and then by processing it, we can choose to, for example, look at the strain transfer from one sensor to the other by subtracting both sensors from each other. And then we get the following graph. So if you look at the bottom joint, which is a healthy joint, you every time see the same pattern coming back. If you would look at the joint who cracked, the crack started at sensor 1 to 2, then it jumps to sensor 2 to 3, 3 to 4, and 4 to 5. So it's also a clear pattern of that crack propagation, which is completely different if you compare that with the healthy joint. We can now look at it in a different way. So here you have how we did it before, but you can also look at the absolute numbers. What is the absolute maximum for a certain load, the absolute minimum for a certain load, and follow that up. You can also look at the slope of each sensor in as function of the load, and then you can see a lot of change happening. We also did Archon sample testing. Archon sample testing is a different test, but it's also a tensile test, but a different sample. You have the sample with the bonded joint, which is also located on one side and on the other side. And it's in the middle, you have a composite sandwich panel, which is glued to the steel part on the top and the steel part on the bottom. On both sides and on the top and bottom side, we foresaw a optical fiber line with multiple sensors included. And this is before the test has done. After the test, we see a clear crack in the bonded joint, and the same is for the back, where you also see at the end of the test, you see a clear crack. If you now look at the samples or the results, you see that on the top, this is the load which is induced into the sample. At a certain point, you get a lowering of that load. If you now go to the sensors, you see at that point that the load increases for that sensing point. You also see that for sensor 5 and sensor 4, and then it comes further than the center line, and then it cracks open until the end. Then we go to in-field application. We have done more testing, and then we decided to try and to see what is needed to install this monitoring system on a real ship. We worked or collaborated with Damen to get this work done. We chose for a ship with a superstructure, which is depicted here in white. Then you have in blue the hull, and these are bonded together. In this case, we chose to mount sensors on the superstructure and to mount sensors on the hull. And at the end, because not only all the sensor results are processed, but we're looking at the deformation, and we also installed accelerometers to look at the loads that the ship is seeing and combine both to say something about the bonded joint. This link is not yet made, but since the results are only obtained a few weeks back. So, but first, what is installed on the hull and what is installed on the superstructure? If you look at the hull has a certain flange on which the superstructure will be installed, and on that one, we installed our sensor line, we installed different sensing points on that flange. Exactly the same thing we did for the superstructure. And in this, you see a little bit, a few of the steps. So if we first start with the hull, we first have a cleaning process, then we go to unrolling the sensor. The next step is then to mount every single sensor point, and at the end we chose to protect the line, the installed line, not from the seawater, but in this case it was a little bit of a mechanical protection to protect it for incidentally hitting the optical fibers during the installation of that superstructure. We also did the same for the superstructure, and must say that this installation happened in one day. So we installed all sensors in one day, and that's of course always needed if you're in a critical part of an assembly or of a production. Same thing here. We first cleaned the sensor and cleaned and roughened the sensor positions. We unrolled the optical fiber. We then glued the sensor points, and we attached a protective tape on top. And then we had to route all the optical fibers towards the front of the ship, and where we install our interrogation unit, and that's installed within the battery compartment of the ship. And we foresee that as a standalone system with a 4G router, so that we could have control over the system from a certain distance. We also foresee that it's linked with the batteries, so as there is a certain testing of power switching off of the ship, that the system is still running. So the results, how does they look like? Well, we did some successful measurement during the sea trials. We did not yet sync in with the accelerometers we had installed, and what we still need to do is relate every event with the measurements, but we can already see a couple of things. And the first thing is this is how the measurements look like during the day. What you see is the measurements on the top are the measurements of the hull, and the measurements on the bottom are the measurements of the superstructure. And you already see a difference between both sensors. And I'm going to explain you now why this is the case. And the first one is that during that day, okay, you start the engine and you go to do the testing, and what you will see is that you get an increase of the temperature within the engine compartment, but probably also in the hold compartment. And that means that you get an expansion of the materials, you get a temperature influence. We said, okay, we chose in this case to do event monitoring and not do absolute strain monitoring. If you would do absolute strain monitoring, you would need temperature compensation to do so. And why now the difference between those measurements in the hull and the superstructure? Well, we have different materials, so different expansion coefficients of the boat materials, and that's what you see in this graph. So we said we're going for event monitoring, and we know what has been happening during that day, during that test day. You have accelerations, emergency stops, you have steer tunings, you have a changing of the RPM of the engine, etc., etc. And you can now look more in detail to all this these results. For example, in this case, you have multiple accelerations and emergency brakes, and you can use that as sort of a fingerprint because they look quite similar. But this you need to combine with the accelerometers. If you then go to, for example, the turning of the ship and you have the superstructure which is going to one side, then what we clearly see, if we take this out and look more in detail to the results, you see that the port side on this side is seeing negative strains, so they are seeing compression, and on starboard side you see the opposite in the sign. So that's clearly showing that the sensors are doing their job in monitoring the deformation of the bond line. We can go a little bit more in detail, and then we see that the difference between sensors that are installed on the hull and sensors that are installed on the superstructure. You see for SH2, S8, SH3, and SS7, you see this kind of behavior, is that the hull is seeing a lot more deformation than the superstructure, which is logic because the bonded joint in this case is a non-structural bond. So you expect this behavior of the boat materials. So this was the end of my presentation, and now going to the conclusions and future work. So if we go to conclusions, what we see is that during the project, we see that we have met the requirements of the marine environment. We played with the raw materials to go for that seawater resistance, to have that heat deflection temperature high enough, and to have a good strain transfer. We also have transferred a repairing technology from a clean lab to an industrial lab, and improved it in that transfer. We showed that it's perfectly possible to monitor cracks in bonded joints, and we also looked at an SHM philosophy where we looked at using finite element simulations to predict what is going on with that bonded joint, and definitely what is going on when you create a certain disbond in those finite element simulations. If you, for example, and this is done together with Bureau Veritas. If you would do a simulation of a superstructure and a hull, and you look at that bond line, and you create artificial disc bonds, what you will see is that, for example, the blue lines are for the superstructure and the colored one are for the hull structure. If you now go from this little blue line, you increase then the disc bond, you create a change in the deformation during hogging and sagging in this case, and it gets bigger and bigger if you make the disc bond longer and longer. Well, what is this the end of the research? Of course not. We have now proven that we can install it on a real application. It's there. We can start to long-term monitor this bonded joint and learn from it on how to further use those sensors in the future. Then this is the end of the presentation, and I would like to thank the Provincie Oost-Vlaanderen, especially for co-funding this project next to Interreg. Thank you for your attention.
Thank you very much, Geert. That was really nice. Do we have questions from the floor? I know it looks complicated. Maybe you can simplify it, because all those signals it's quite a lot to take in. So, like would the end user or people who are using them in practice would be able to interpret that data, or it's.
But what I tried to show is that you have always raw data results which you need to combine and to say something on the health of a structure. It's not by just looking at the data. For example, for this data, the first thing you do is stare at the screen for an hour, and then you start seeing the patterns. And it's of course the next step is to interpret those patterns and to make an algorithm of it. That's for sure. Yeah.
Yeah. Linda, please go ahead.
Hi. Sorry, it's more of a statement really than a question. I think what Dimitris and Geert have shown is that how important it is that we actually think about structural health monitoring and non-destructive testing whilst we're doing the design. Quite often we're submitted applications where it's kind of an after effect is, and we'll do some structural health monitoring or NDE at some point. But I think they've both shown that actually involving that during the testing regime not only tells you, gives you information that you can use then in service to identify and characterize damage, but it'll tell you more about the testing that you're doing in the first place. So I think it's really important, just involve these guys as early as you can in your process, and it's you'll get a lot more use out of what you're doing.
Yeah, what I perhaps like to mention as well is at the end it's structural health monitoring, but in the beginning it's a validation of your design. It's looking at the finite elements that Frans has shown and how well is this fitted now in the real application. Do you measure these deformations? What is happening? And use those data to improve your design, to improve your bond.
Yeah, that's really important. Yes, we have a question. Yes, Frans.
First of all, again, thank you for the nice presentation. Now, I have this question related to the measuring of signals, the complexity of actually interpreting them. Now, when we look into health science, healthcare, and the whole concept around that one, there has been the application of artificial intelligence, neural networks that actually collect the data and can pick up tiny signals that a human can actually not pick up. And based on those signals, decisions are made that save lives. Do you think there might be also an application in this case that you employ some artificial intelligence, neural networks that are being trained while being in operation conditions, so it's kind of self-learning, and they improve over time?
Yeah, I think so, but you need a combination, of course, of different signals. It's not going to happen alone with strain measurements, but you will also always need to know what is the load acting on that chip. For example, with accelerometers. But in one of the testing, you've seen the tensile test, where you have the top joint which cracked and the bottom joint which stays healthy, and there you see clear patterns occurring, and you could use this mechanisms in artificial intelligence. Could of course be the next step. I'm not an expert. But then we need someone who is experienced in that topic.
And there's a funding coming up, right?
Yes, we do it.
We definitely will.
Yep.
Thank you. Okay, do we have more questions? Yes, please, come up.
So, thank you, Geert, for your presentation. So, nowadays there are many techniques to measure the strain in a service life during the structure. But I'm just wondering how a BG sensor strain measuring technique is different than the strain gauges.
I tried to explain in one of the slides, but I can definitely repeat it. Is that you have several advantages over electrical strain gauges. One is electric, and the other one is a passive component. But the main advantage is that you don't need a calibration or recalibration over the life. So it's not dependent on how you connect your strain gauges. No, your optical fiber. It's related with the wavelength which is back reflected, which is an intrinsic parameter of that sensor. And as last advantage is that you can have multiple sensors in one line. Which really ease up the installation process. Like you saw on the ship, in that case, we installed 20 sensor points in only one day. And we could, at that point on, already start measuring if the ship was ready, of course. So it's really makes life easier in installation.
Thank you.
You're welcome.
I have a question. I don't know if you mentioned this, but for how long would you say you can use these sensors? Like, you don't need to go and change them, because I saw you put them inside, so it's in.
Well, in the ship, you can still access them if you remove a couple of panels, but you will probably not be able to repair as such. I think you can put extra sensors still if you would if it's needed. But what you do is you try to make it for the rest of the life of the ship, of course. And in this case, it is really on the flange. It's behind panels. Nothing, except perhaps for a rat, nothing can happen. I must say, I once saw sea stars eating or cover, so everything can happen. So you really have to be prepared for that as well.
But they are designed to be long-term sensors.
Yeah,
so
true.
yeah,
Yeah,
okay.
yeah, true.
Great. Thank you. Thank you very much, Geert.